So I'm going to talk about a method called Bender's decomposition. And we've been telling you about methods for mixed integer nonlinear optimization, such as branch and bound and outer approximation. Bender's decomposition is not as old as branch and bound, but older than outer approximation. So the problem that we're solving is still a mixed integer nonlinear optimization problem that I've written here, where we minimize this linear objective function eta that's supported by a nonlinear function. So that was the trick that we used earlier to linearize the objective function. And we have some nonlinear constraints and then integrality on the second set of variables. And we assume that our problem is nice, that it is a convex mixed integer nonlinear optimization problem. So the functions f and g are smooth and in particular convex. And we assume that we have a constraint qualification. And then an additional assumption is that the feasible set is bounded. So either we are given lower and upper bounds on our variables so that we work in a box, or there's some other condition that holds that ensures boundedness. And we need the boundedness to make sure the algorithms are finite, and the smoothness and convexity, or the convexity in particular, ensures that the cutting planes that we generate are valid cutting planes, and the smoothness and constraint qualification is needed to ensure that the nonlinear solvers are converged when we solve subproblems where we either fix the variables or relax integrality. Okay, so there are two very broad classes of methods for solving mixed integer nonlinear optimization problems, and you've already seen one example from each class. So there are single tree methods. Those are methods that create and search just a single branch and bound or branch and cut tree. And the examples are, for example, nonlinear branch and bound, which we saw yesterday, LO-NLO-based branch and bound, which I will show you later today, and nonlinear branch and cut. And the key part is that they build just a single tree. In contrast, there are also multi-tree methods, and those are methods such as outer approximation, which we saw yesterday, and Bender's decomposition, which I'll introduce today. And there's another method called the extended cutting plane method, which we won't get into detail too much. So the nice thing about multi-tree methods is that they only ever evaluate the integer variables or functions of integer variables at integer points. So that's very important if you can't evaluate functions at relaxations, for example. And here's a cartoon of what these methods look like. You have some initial nonlinear optimization problem that you solve. You set up an initial branch and bound tree. You solve this. You get a new assignment of integers, and you return and create and solve another branch and bound tree. And so one of the bottlenecks is that these MILP or MILO branch and bound trees cannot be restarted. So once you've set it up and solved it, you lose all the information for the second time round, and you create everything from scratch. Whereas these other methods only use a single tree. And the methods are good in certain cases and other cases. So it's worthwhile trying out which method you want to use on your problem, and that's why we're using AMPL, a modeling language, so that it's easier to switch solvers. The reason for multi-tree methods, or the original motivation, is that mixed integer linear optimization is much better developed than nonlinear optimization. And in particular, linear optimization problems can be hot started. You can reuse the factorizations. You can do a dual simplex method. And the same is not true for nonlinear optimization problems. You need to change the method in order to be able to do that. There's also been now decades of investment into software for mixed integer linear optimization, and I'll show you later how you can exploit that for developing new methods. And of course, it's much easier. You don't need a constraint qualification. So if you're worried about constraint qualification, this is a much better developed tool. And there are these three broad sets of multi-tree methods. There's outer approximation, which you heard about yesterday, Bender's decomposition, which you'll see in a moment, and the extended cutting plane method. And again, just to emphasize, multi-tree methods only evaluate your nonlinear function at integer points. So that can be advantageous if you cannot relax this integrality constraint. So there are two problems, subproblems that we need to define in order to define Bender's decomposition, and we had those yesterday as well. There's the nonlinear optimization problem up here, where I fix the integer variables. So this is a problem that's parameterized in the integer variables, and it's a problem where I just minimize over the continuous variables only, subject to the nonlinear constraint. And this problem has an optimal value that corresponds to whatever integer you plug in there. You use the same notation for the optimal value that comes out. But in general, nonlinear optimization problems may not be feasible, and detecting whether a nonlinear optimization problem is feasible or not is just as hard as solving a nonlinear optimization problem. And so if the problem is not feasible, if the nonlinear optimization problem is infeasible, then we split the constraints into feasible constraints and infeasible constraints. And what we do is we keep the feasible constraints as constraints here, and the infeasible constraints, so those are the constraints which are positive at the solution, we just sum them up in the objective function. And we minimize the violation, so the amount by which these constraints are positive. They're supposed to be non-negative, so we minimize the positive part of these constraints. And solvers do this in different ways, but if you want to prove, if you want a certificate that your nonlinear optimization problem is infeasible, then you need to solve such a feasibility problem. So there are other methods, such as penalty function methods, but they don't provide a certificate of infeasibility unless the penalty parameter goes to infinity. And that's really hard to do on a computer such as this. Letting things go to infinity usually turns nasty. So you don't need to read papers on Bender's decomposition. You can just learn Bender's decomposition if you know outer approximation and this very little or this very simple trick. So let us assume that we have solved a nonlinear optimization problem where we fixed the variables and we obtained a solution xj and some optimal Lagrange multipliers corresponding to the inequality constraints. And then we can just write down the outer approximation cuts that we would generate. So those are the first order Taylor expansion of my objective function here about this point xj. And I apologize, this should actually be a yj down here. This should not be an xj. And you also write down the first order optimality, sorry, the first order Taylor expansion with respect to the constraints. And then you do this little trick. You create a new constraint by summing all of these constraints. The first one weighted with 1 and the other one's weighted with the optimal Lagrange multiplier. And because this multiplier is non-negative, this gives you a valid inequality, so I don't have to change the signs here. I have a new valid inequality. The first part is eta, because lambda j transpose 0 is eta. And then for the second part, I use the fact that the complementary slackness holds at my solution. So when I multiply lambda j with gj, I get a 0. So that's why I don't have a constant term here. And then if I add the first order conditions, I see that the gradient of the Lagrangian with respect to x, which is this part here, also vanishes because I solved my nonlinear optimization problem to optimality. So all I'm left with then is this little cut here that now only involves the binary variables. So this is the Bender's cut. You can show that this is entirely equivalent to the Bender's decomposition that Geoffrion and others have developed, and this is exactly the cut that you need. So this is nice because the cut is a cut in integer variables only. So this Bender's master problem that we're going to write down next will have one continuous variable and all the other variables will be integer. So that could potentially be a smaller problem, especially if you have a lot of continuous variables and only a few integer variables. Then this could be a really nice approach. Okay, And you can do a similar thing for the feasibility problem, and I made the same mistake here. So this should again be a yj, not an xj down here in the second term. It's a first order Taylor expansion, and you do the same trick. You solved your nonlinear feasibility optimization problem, and now you have infeasible and feasible constraints that are indexed by I and F, and you sum them all up. And if you do that, then again you get this cut down here. You have a 0 on the left-hand side. E is the vector of all ones. You get, again, that the gradient of the Lagrangian with respect to x will vanish. So that means you get rid of the x components here, and you're just left with the y components. But in this case, because these constraints are violated, and you multiply them by a 1 each, this is actually the summation of the violated constraints. And there's a simple corollary that you can just write down immediately, which states that this cut eliminates the integer variable yj. And so do you see why that's happening? Does anybody know why that's happening? Corollary, the Bender's cut, or the Bender's feasibility cut, eliminates yj infeasible. And the proof, it's really just a single line. We just substitute y equals yj, and then we get that the second term here will vanish because y is equal to yj, and we just have 0 greater or equal to the sum of I for the infeasible constraints, gi of yj, and we know that this is positive. And so there you see immediately that this constraint ensures that you will never go back to a yj that you decided was infeasible. So that's good. You do want that. Okay, so here's sort of the master problem now and the sub-problem that you're solving for Bender's decomposition. So first of all, each time you solve a nonlinear optimization problem, you can update your upper bound. So the upper bound is just the smallest objective function value for all the nonlinear optimization problems that you've visited that is feasible. So if you're at iteration k, then you look through all the previous iterations and you just keep track of what the smallest objective function value was that you encountered along the way. And then we can, similar to outer approximation, we can then define a Bender's master problem. And this Bender's master problem now has the Bender's optimality cut, that's his first cut here, and the Bender's feasibility cut. And you can, the notation here is probably not clear, but the first set of yj are those that are feasible, the second one are the ones that are infeasible. So you're either at a feasibility cut or an infeasibility cut. The infeasibility cut doesn't do anything for you if the problem is feasible, because in that case the summation would be 0 and it's just a vacuous cut. So you wouldn't add this. And so the key is then we have now a relaxation where we only have a subset of the cuts that we generated, and we can solve this in an iterative algorithm. So here's a sort of cartoon of what's going on. I start off by having just one cut that I obtain by solving the initial nonlinear optimization problem at this point here, and I generate a supporting hyperplane on my nonlinear objective function f. Then I do my branch and bound tree search here. I generate a tree search, and I find a now new integer assignment that's going to be this one over here. So then I go back in, I solve another nonlinear optimization problem, and I can generate another cut. So this would be this one here. And I can just keep going around this. Now I again set up an MILP that I can solve, and I can go around this loop. So here's what the algorithm would look like. You're given an initial guess, and that's where you first evaluate, where you generate your first cut. And then you solve either the nonlinear optimization problem or the nonlinear feasibility optimization problem, and you get a solution that corresponds to this integer point. If this problem was infeasible, if it was feasible, and if its objective function value is less than your upper bound that you set here, then that means you have a new incumbent. This is your new best solution because it's lower than the upper bound, which is the value of all previous solutions, or the lowest value of all previous solutions. Otherwise, you just leave the bound unchanged. You linearize the objective and constraint functions about the new point. You add this point to your collection of master problems, and you solve the master problem. And you just keep going round in this loop until the master problem is infeasible. And so my stopping criteria is different here to Ashutosh's, but they're really equivalent because if I go back to my master problem, I added this upper bound on the objective function to my master problem. So once I cannot find a lower bound that's below my upper bound, then this problem will be infeasible. And so that's an alternative way of writing this problem, but you could also just look at the bounds. And to be honest, I think that looking at the bounds is better because you avoid having to tune this constant epsilon that you have to tune it depending on the solver otherwise. Okay, so here's a quick exercise. It's not so quick actually, but how do we solve these nonlinear optimization subproblems? So typically you have a solver, a nonlinear optimization solver. You provide the problem to it through AMPL, and the nonlinear optimization solver will actually see the full problem. So it will see both the continuous and the integer variables, but it doesn't regard the integer variables as integers. So here's an alternative way of setting up the problem. Rather than fixing the integer variables and substituting them into the nonlinear expressions, I can just add an additional constraint that says y has to be equal to yj. Okay, that's entirely equivalent. The y cannot move anywhere, even if I'm now minimizing over y. Y is sort of chained, attached to the value yj. So it will never move away from there. So this problem is entirely equivalent to the problem where you substitute them in. But this is actually easier because you can just fix those bounds in the interface to the solver. And that's actually a much better way of doing it. Now here's a little trick. And if you look back at the Bender's cut, the way I derived it here, I told you, create the outer approximation cuts. Then you're going to sum all these outer approximation cuts. And then you need to compute the summation and get your cut. So this is quite a bit of work, right? You have to evaluate, get these gradients somehow, sum them all up, make sure you don't make a mistake. There's an easier way of doing it, which is the solvers will return to you a Lagrange multiplier of this constraints. And it's easy to show that the Bender's cut is actually equivalent to just this cut here. And so you don't need to get the gradients, you don't need to sum up the gradients, you don't need to do any of that. You get this cut for free. And you even get this cut when you're doing outer approximation or any other method. If you're using this subproblem, the Bender's cut is always immediately available to you. You can always use it. So even when you're doing outer approximation, you can switch, right? You can say, I'm going to use an outer approximation cut here. I'm going to switch back to Bender's cuts. Okay, quick question. Has anybody solved this exercise yet? Or were you all just paying attention to me at the front? Anybody got an idea on how to do this? what should we do? So one way to do this would be to write down the first order optimality conditions. So I'm going to try to do this on this little piece of board there, but I can also switch off the monitor, up the screen. Okay, so let's write down this problem again. We minimize f of x and y over x and y, subject to the constraints g of x and y less than or equal to 0, and y, I'm going to write this different, y minus y j is equal to 0. Okay, so then I'm going to assign multipliers and form my Lagrangian. So the multiplier that I'm going to use here is going to be my friend lambda j, and here I just use the next letter in the Greek alphabet, mu j. So then my Lagrangian, that now depends on x, y, lambda, and mu, is given as f of x plus lambda transposed g of x and y plus mu transposed y minus yj. Okay, bless you. And so the first order conditions for this problem in now x and y, we'll do those separately, is that the Lagrangian with respect to x vanishes, which gives us, I'll just look this up, the gradient with respect to x of f plus the gradient with respect to x of g times lambda is equal to 0. And then I have a second gradient condition for the second set of variables, which are the y's. And this looks almost the same, plus the gradient of, with respect to y of g, I think there's a transposed here, times lambda. But now I have one additional term. I have my mu here. And I did this the wrong way round. I should have written this as minus mu plus y. So if I write it like this, then it's going to come out nicer. So then I get a minus mu here. And this last constraint, I can just rewrite it as mu is equal to grad yf plus gradient with respect to y g times lambda. And those were the coefficients in the Bender's decomposition that I showed you. So provided you do this the right way around with the sign, and I apologize for not doing this the first time right, you get out of your first order conditions for the nonlinear optimization problem that you read up the multipliers, and those are the Bender's cuts. Okay, so that's all I wanted to say about Bender's decomposition. The cuts themselves are typically weaker than outer approximation cuts because they're a linear combination of these outer approximation cuts. And so there's some cancellation that happens. The Bender's cuts are always, they tend to be dense. So they are weaker than outer approximation. The cuts are typically dense. So that means every entry in mu or in this gradient is non-zero. And that affects how the solvers in some ways. But the convergence follows the same. So you get the same convergence as, or the same convergence theory as outer approximation. It's exactly the same mechanism, so that's nice. And so you terminate finitely, and Bender's decomposition is a finitely terminating algorithm, just like outer approximation. Okay, so with that, we'll take a short 5-minute break unless there are questions about Bender's decomposition. If not, let's take a 5-minute break. Come back and I'll tell you about the best algorithm for solving mixed integer nonlinear optimization problems in the next lecture. Thank you.
So here typically there is only one cut which is added every time we solve.
Yeah. There's only one cut that's added once we solve NLO. That's, yeah.
Whereas in OA we just add.
In outer approximation, you add one cut for the objective and then one cut for each of the constraints. And so, and these cuts could be much sparser often, but if you sum them up, the sparsity patterns start to overlap, and then this cut becomes dense. That's the Sorry?
What is the advantage over outer approximation?
So one advantage is that if you had a lot of continuous variables but very few integers, then this might be more efficient. In general, it's not better. But we're going to use these Bender's cuts also to condense outer approximation cuts once they get out of date. So that's happening in an hour. So not the next lecture, but the lecture after that. You can use this trick to condense cuts and without losing convergence, for example. That's a really good question. So the way I was doing it is I was solving the problem and assuming that I know. What happens when you solve nonlinear optimization problems, the optimality solver will actually terminate and tell you, here's a set of constraints I cannot satisfy, here are the constraints that I can satisfy. So the solver does that for you. Now, you could ask, how does the solver identify this? And the way I do this is by looking at the local approximation that I'm solving. So I have an iterative method, and on each iteration, I divide my constraints into feasible and infeasible ones. And then I have some mechanism of changing those around. And there's a proof that I then eventually identify the violated constraints, that set of violated constraints will eventually be stable, and so the last few iterations are then just fast convergence to those points. There are some papers on how to do that. You can also set up a minimization of an L1 sum of the constraints, and then you will there you can show that the L1 norm will help you identify and finds a small set of infeasible constraints. So you can have an L1 norm feasibility problem, which is, in this case, would be minimize the one norm of g of x and y, which is defined as the sum I equals 1 to m of the absolute values of gi of x. So when you solve this problem, the one norm has one norm is sparsifying, or is a sparsifying norm. And it will, if the problem is infeasible, then it will find the ones that are preventing it from becoming feasible, or a superset of the constraints that prevent it from becoming feasible. And the sets are not unique, so there could be problems where the sets are not unique and you just converge to one of them, but that doesn't matter. Yeah, you solve this iteratively for all constraints. You don't have to do that, actually. The nonlinear solvers already do this. So the solve for NLO already includes this. So you don't need to worry about it. You're not really good solving two problems. I'm just setting up two problems here so that I can talk about the notation and the difference between the feasibility and the optimality cut. But the solver will tell you at the end, when it terminates, whether it's feasible or infeasible. And you can try that out again in AMPL. You can take a problem that's feasible and add a constraint that doesn't make any sense. For example, x1 squared plus x2 squared less than or equal to minus 1. So the solver will detect that that's nonsensical. Or you can do something better. You can maybe do that and x1 minus 1 squared plus x2 minus 1 squared less than or equal to a half. So you're looking for the intersection of two circles, one around the origin and one around the point 1, 1, but the radius is just not big enough. So if we can make this a half as well, for example. So set this up in AMPL, and it will come out, and depending on the solver, it will either identify this one is feasible and this one is infeasible, or the other way around, or it might tell you both are infeasible. And that depends on the nonlinear solver that you're using.